Have you ever wondered how the laws of nature are described? How do we make sense of the intricate motions of objects, from the graceful flight of a bird to the precise orbits of planets around the sun? Behind these phenomena lies a profound mathematical framework known as the Lagrangian formalism. Welcome to a captivating journey through the world of Lagrangians, where we'll uncover the hidden beauty and elegance of the universe's behavior. Throughout history, brilliant minds like Isaac Newton and Albert Einstein have strived to comprehend the fundamental principles governing the cosmos. Their groundbreaking contributions led to the development of Lagrangians, a mathematical approach that unveils the underlying laws that shape our reality. At its core, a Lagrangian is an expression that summarizes the energy of a system in terms of its coordinates and velocities. It captures the essence of motion and provides a powerful tool for understanding a vast array of phenomena, from classical mechanics to quantum field theory. Lagrangians allow us to explore the intricate dance of particles and forces, revealing the paths they follow and the interactions they experience. With Lagrangians, we can unravel the mysteries of the smallest subatomic particles and decipher the grandeur of the cosmos. Join us on this adventure as we embark on an exploration of Lagrangians, unraveling the secrets of motion and discovering the hidden harmony that governs the universe. Prepare to be captivated by the elegance and power of the Lagrangian formalism as we delve into the heart of nature's symphony. Certainly. Let's dive into a detailed explanation of Lagrangians. In physics and mathematics, the Lagrangian is a fundamental concept that plays a central role in the Lagrangian formalism, a powerful mathematical framework used to describe the behavior of physical systems. It provides a concise and elegant way to analyze the motion of objects and understand the underlying principles governing their behavior. At its core, a Lagrangian is a mathematical function that summarizes the energy of a system in terms of its coordinates and velocities. It encapsulates the dynamics of the system and contains all the essential information needed to determine how the system evolves over time. To understand the Lagrangian concept more concretely, let's consider a simple example: a pendulum. The pendulum consists of a mass attached to a string or rod, which swings back and forth under the influence of gravity. To describe the motion of the pendulum using Lagrangians, we need to define a Lagrangian function. The Lagrangian function for the pendulum takes into account the kinetic energy, energy of motion, and potential energy, energy associated with the height of the system. It is formulated as the difference between the kinetic energy and the potential energy. L equals T, V, where T represents the kinetic energy and V represents the potential energy. The kinetic energy of the pendulum depends on the mass of the object and its velocity, while the potential energy depends on the height of the object and the gravitational constant. By plugging in the appropriate equations for the kinetic and potential energies into the Lagrangian function, we obtain a concise expression that fully describes the pendulum's dynamics. Once we have the Lagrangian function, we can derive the equations of motion for the system using a principle called the principle of least action, or the principle of stationary action. This principle states that the actual path taken by a system between 2 points in space and time is the one that minimizes or maximizes the action integral, which is a mathematical quantity defined in terms of the Lagrangian. By applying the principle of least action, we obtain a set of differential equations known as the Euler-Lagrange equations, which describe the system's motion. Solving these equations allows us to determine the trajectory, velocity, and other properties of the system as it evolves over time. The power of the Lagrangian formalism lies in its versatility and applicability to various branches of physics. It is not limited to classical mechanics, but extends to other domains, such as electromagnetism, quantum mechanics, and even relativistic physics. In each case, the Lagrangian function is tailored to the specific system and its governing laws. In summary, Lagrangians provide a profound mathematical framework for understanding the dynamics of physical systems. By encapsulating the energy of a system in a concise function and applying the principle of least action, we can unravel the intricate motions of objects, from simple pendulums to complex quantum particles. Lagrangians unlock the hidden beauty and elegance of the universe, enabling us to decipher the fundamental laws that govern our reality. In the Lagrangian formalism, the mathematics revolves around the concepts of variational calculus and the principle of least action. Variational calculus deals with finding functions that minimize or maximize a certain mathematical quantity, known as a functional. In the case of Lagrangians, we see the path that minimizes the action integral. Let's consider a system described by generalized coordinates q, t, where t represents time. The Lagrangian function, denoted as L, is defined as the difference between the system's kinetic energy, T, and its potential energy, V. L q dot q t equals t q dot q t v q t, where q represents the time derivative of q with respect to t. To describe the dynamics of the system, we introduce the action functional, denoted as s, which is defined as the integral of the Lagrangian over time. Sq equals int t1 t2 L q dot q t dt, where t1 and t2 are the initial and final times, respectively. The principle of least action states that the true path taken by the system between the initial and final times is the one that minimizes the action integral. In other words, the actual path satisfies the condition that the action is stationary or extremal. To find that path that extremes the action, we employ the Euler-Lagrange equations. These equations are derived from the principle of least action and provide the necessary conditions for the Lagrangian to be stationary. The Euler-Lagrange equations are given by frac d dt left, frac partial L partial dot q right, frac partial L partial q equals 0, where frac partial L partial dot q represents the partial derivative of L with respect to dot q, and frac partial L partial q represents the partial derivative of L with respect to q. Solving the Euler-Lagrange equations yields a set of second-order differential equations that describe the motion of the system. These equations fully capture the dynamics and determine how the generalized coordinates q, t evolve over time. In practical terms, solving the Euler-Lagrange equations involves substituting a Lagrangian function into the equations and performing the necessary differentiations and manipulations. The resulting differential equations can then be solved to obtain the desired solution for the system's motion. It's important to note that the Lagrangian formalism is not limited to classical mechanics. It can also be extended to other areas of physics, such as electrodynamics and quantum field theory. In these cases, the Lagrangian function is tailored to the specific system and incorporates additional terms and fields to capture the relevant physics. In summary, the mathematics of Lagrangians involves variational calculus, the principle of least action, and the Euler-Lagrange equations. By formulating a Lagrangian function and applying the principle of least action, we can derive the Euler-Lagrange equations, which describe the motion of the system. Solving these equations allows us to determine the trajectory and behavior of the system over time. The creation of Lagrangians is a fundamental concept in the field of theoretical physics, specifically in classical mechanics and quantum field theory. The concept was introduced by Joseph-Louis Lagrange in the late 18th century as a mathematical formulation to describe the behavior of physical systems. The Lagrangian provides a concise mathematical description of the system's dynamics and is a key ingredient in the development of the principles of least action and variational calculus. To understand the creation of Lagrangians, let's start with the principle of least action. This principle states that the actual path taken by a physical system between 2 points in space and time is the one that minimizes the action integral. The action is defined as the integral of a quantity known as the Lagrangian, denoted by L, over a certain region of space and time. The action integral is given by S equals L dt. Here, S represents the action, L is the Lagrangian, and the integral is taken over the time interval during which the system evolves. The Lagrangian is defined as the difference between the kinetic energy, T, and potential energy, V, of a system, that is, L equals T, V. However, this is a simplified form and can be generalized to include other terms depending on the specific physical system under consideration. In classical mechanics, the kinetic energy of a system is given by the sum of the kinetic energies of its constituent particles. For a single particle with mass m and velocity v, the kinetic energy is T equals 1/2 mv2. The potential energy, on the other hand, depends on the forces acting on a system and can take various forms. For example, in a gravitational field, the potential energy of a particle of mass m at height h is given by v equals mgh, where g is the acceleration due to gravity. To construct the Lagrangian for a system, we need to identify all the degrees of freedom that describe its behavior. In classical mechanics, the degrees of freedom are often associated with the positions and velocities of the particles in the system. Each degree of freedom corresponds to a coordinate variable, q, and its associated velocity, dq/dt. Once the degrees of freedom are identified, the Lagrangian can be written as L equals T, V, where T and V are expressed in terms of the coordinates and velocities of the system. However, it is important to note that the Lagrangian must be expressed in a coordinate system that is appropriate for the problem at hand. This choice of coordinates can greatly simplify the equations of motion and make the calculations more tractable. In quantum field theory, the creation of Lagrangians follows a similar principle, but with additional considerations. Quantum field theory describes the behavior of elementary particles and their interactions. The Lagrangians in this context incorporate the principles of quantum mechanics and special relativity. In quantum field theory, the Lagrangian describes the dynamics of a quantum field, which is a mathematical object that describes the behavior of elementary particles. The Lagrangian density, denoted by L, is a function of the field variables and their derivatives. The action integral is then given by S equals LD for x. Here, L represents the Lagrangian density, and the integral is taken over space-time. The Lagrangian density in quantum field theory can be constructed to incorporate the interactions between the fields and their corresponding particles. The precise form of the Lagrangian density depends on the specific field theory being considered, such as quantum electrodynamics, QED, quantum chromodynamics, QCD, or the standard model of particle physics. In summary, the creation of Lagrangians involves identifying the degrees of freedom and constructing a mathematical function that incorporates the kinetic and potential energies, classical mechanics, or describes the dynamics of quantum fields, quantum field theory. The Lagrangian provides a compact and elegant formulation of the dynamics of physical systems and serves as a foundation for the principles of least action in variational calculus. Goodbye.